I want to show you a little bit of something. This is really something I prepare for the statistics sort of class, but I want to contrast a little bit of where we are. And oops. Right. Okay. Now, we talk a great deal about the data and so forth in the beginning, right? And I just want to show you that when it comes down to analysis, again, referring to my earlier slide, it's in your computable notebook, but here I just put it as a mind map. The three problems, right? So in modeling, what you're trying to achieve, in optimization, what you're trying to achieve, and optimal control, what you're trying to achieve, right? Now, in optimal control, mainly it's about stability and sustainability of the system. Sorry, how do I get rid of this thing? Okay. In optimization, you sort of like try to improve the performance outcome to the best that you can. Most of the time that we are dealing with, we'll start with modeling aspect, right? And what are you trying to do? You're trying to solve some kind of problem. You're trying to find some kind of solution, or you're trying to gain some insight, some competitive edge, right? And the notion I want to introduce today, it's fairly informal, right? But I want you to get an idea. If you want to gain information or gain insight, it's about model building. It's like, you know, how X leads to Y, or how do you know more about this and that? It's about gaining insight. You kind of build the model to have a description of the reality you're trying to understand. When you're solving a problem, you're actually doing the opposite. You're inverting the problem. It's like if you have X and once you know X, you can know Y. Then you flip the question around. You say, well, if I had Y in mind, right? What is the X that's going to get me there? Okay, that's the flip side. It's a solving. And a lot of time I don't really mention this is because it occurs a lot more within the context of optimization. Because what you want is not any Y, it's the best Y, right? So given an X, the model will generate a Y. The inversion say, if I had in mind this kind of Y, what kind of X will get me there? Okay, and in modeling that happens, but a lot of the time it happens within the context of optimization because you have Y star, the best Y there is. I want to get the best outcome there is. What is the combination or input that will get me there? That sort of thing, right? So I just want to add that we are more or less in the business of the forward pass, of building the model, okay? And I kind of generically put, actually there in the mathematical note, in the computable document format note, you see that there are three modes of learning, like identification. I leave that out for now. But basically the distributional learning, okay? The distribution learning is sort of like, where are the X's? Okay, where are the X's? Right? X is your population of attributes, right? Who are my clients? My clients have certain attributes. What is the population? What is the world data? What are the countries? Each country has its own data vector and so forth. Now, I would say with some rough generalization that you tend to fall into this kind of analysis, where the X's will be like distribution analysis, right? And that most of the time, okay? Now this is not a must, this is a most of the time thing. Most of the time, distribution analysis will be handled by statistical method, right? And that's what we covered, I think, 3 classes back. And that's also something you probably covered in the first year, okay? Where are the X's when you don't have an assumption on what the distribution shape is, but you sort of want to learn about where the clustering are? That tends to be done here in machine learning. In fact, that's today's topic, okay? So this here, if I put another thing and say by unsupervised learning. Okay. Now, if the problem was, let me get rid of this so I can move. On my screen, there's a black tab that I can't get rid of. Hold on, just a second. Oh, gotcha. Okay. This kind of relationship, if I knew X, what do I know about Y? Again, comes in sort of two problems, regression analysis and classification, right? And we talked last time, right? What's the main difference between regression and classification analysis? If it's regression, the output is numerical and then basically something that belongs to a interval or ratio scale, right? Whereas classification analysis, it's A or B or C or D, right? And most of the time it is nominal, meaning that A and B are just different. Nothing is better. But sometimes you do have something like A is bigger than B. So that's ordinal. And sometimes ordinal is handled by regression kind of method. So it's sort of like halfway. I'm not, it depends. So it's no hard and fast rule. But anyway, I just want to show this picture and have you have that memory committed to your memory a little bit. Again, this is not always the case, but it tends to be. It tends to be that if you talk about distributional analysis, it's mostly statistical method. Cluster analysis will be by what we are learning today, which is machine learning. If you talk about regression analysis, like, given X, what are the Y's, and Y is interval or ratio scale, numerical, then you do have statistical method, linear regression, right? And then you have machine learning, and that's everything we learned last week, and also we will be learning more. There's a lot more. There's a lot more. Last week is just a taste of what's to come. Okay. We're dealing with a huge number of data, and it does give you insight. So before I do this, I'm going to go back to old-fashioned data mining. Okay, this is what data mining looked like maybe in the 80s, but it's still used today. Okay, I'll give you a little story first, because everybody likes a story. Apparently, and I think there's an element of truth. It could be a apocryphal story. It's something like Target or something. Yeah, Target analyzed using this kind of data mining, this kind of counting techniques, and came with the conclusion that a young woman, a young girl who's not married at the time is going to have a baby, and start sending coupons or diapers and stuff like that to the house, right, in the name. Yeah, and this is done by pure association alone. The counting gives you that association, and I think the dad is very angry, right? My daughter is not yet married, why is she going to have babies and so forth? And before I have to talk to the store manager, I don't know, Walmart or Target, I don't know what. Okay. Well, it turns out in a few weeks, the store was right. He was actually, having a baby, and so he literally apologize to the store. So apparently the store knew his body was having a baby before he did. Okay, or he did just from her shopping behavior alone. Okay, now this is not powerful because the mathematics is powerful. It's powerful because it is a retail application where you have thousands and thousands of items and thousands of customers a day. It's the volume game. Okay, it's the volume of data that allows you to do this kind of stuff. So, in essence, we have this kind of four standard kind of analysis in data mining. Okay? One is called frequent item set mining, one is called association rule mining, one is called sequential pattern mining, one is called sequential rule mining. Okay? What is an item set? Well, item set is a basket. It's a basket. So I'm not going to write any of this down because it's easy in your head. Again, in real life, it will be thousands and thousands of products. So let's say you have a supermarket. Okay, so it has 50, 100 items, right? A basket is when one person takes a basket and puts in the item. Now, in this case, the number of items doesn't matter. So if you buy 3 Coke, right? Buying 3 boxes of tissue, okay? So, what is it? Well, if you have 100 items to buy, what can a customer carry? Just figure 100. A basket can contain nothing. A basket can theoretically contain 100 different products, right? Or any combination in between. Okay? This kind of combination, how many do you think there are? How many? How many combinations of baskets? Let's say if I have a basket that has an apple, a banana, that's one. Basket that has apple, orange, and banana, that's another one. How many possible combinations do you think there are? It's 2 to the 100. Because think about it, a basket is there, right? We have the first product, it can be there, it may not be there. So that's 2 combinations. So the next product, it may be there, it may not be there. That's another 2 combinations, 2 times 2 is 4, right? You have 3 products, it's 2 to the power 3 and so forth. This, by the way, is called the set of all the subsets, is called the power set. Okay, and let me show you, just for fun, subset, okay, range, if I give you something like range 5, okay, that is a number from 1 to 5, right? If I say subset of range 5, that gives you how many combination? How many? Quick. 32. Right? 32, right? Okay. Now, I'm not going to print all, but let's say I have 100. Okay. I want to count how many items I could. I'm not going to print. I'm just going to find the link. Too large, must be machine integer. See, 2 to 100 is not handled in your computer, right? So it's very difficult. So that's why this is something that is an opportunity. If you are Walmart, if you're Target, you have lots of data. It's also a challenge, and it's also a barrier of entry, because if you're just a mom and pop shop and you didn't have this mathematics or algorithm, you couldn't deal with them. And if you have the mathematics, you don't have the data. Right? So it's a barrier of entry. But let's say you have 50. Let's see if that's, oops, sorry. Let's see if 50 is handled. Say 20. I think 20 is okay. There. There's a million combinations because that's 2 to the 20. Right? That's 2 to the 20. That's a lot. Okay. So we're not going to catalog them all. Okay. Now, let's say let's say for all practical purpose, a basket can only carry 5 items. 5 items. Then I put like a maximum here, like 5. Then it, you know, the number of combination goes down. So basically, you can have 5, you can have 4, you can have 3, you can have 2, you can have 1, you can have 0, and have 6, or all the way up. So that's the idea. Now, so yeah, you have 100 products. You have, let's go to 20 products. Yeah, you have 20 products, of which there are 1 million combinations. Yeah, yeah. You have 7 and 11 so for this small shop, 20 products. That alone generates 1 million combinations of baskets. Yeah. Now, frequent item set is that basket. It's item set of items. Frequent means how often do you see one of these? In other words, you obviously maybe see something like apple and bananas in a basket more than, say, kale and cigarette. Yeah? Kale is what health conscious people, right? Health conscious people don't smoke. So it's not likely you're going to see kale and cigarette in the same basket. That's it. Okay? But you can certainly see cigarettes and alcohol. Okay? Or you can see kale and tomato juice and flaxseed or something together, right? So this is the frequent set analysis. It's like counting. If you have database of, you know, 5 years worth of people coming into Walmart, and you have millions of customers, what is the really popular product? What's the combination? Not just each popular product, because you can just do that by ranking, right? By the inventory check, right? What sells the most? Say you sell soda the most. That's obvious. It's the combination they want. Yeah? And this is why it's so powerful, because it determines exactly where they put stuff in the supermarket. Okay? You ever wonder why certain things you want to buy together are not put close to each other, even though they are logically similar? For example, let's say milk and cereal. Very convenient, right? So a convenience store will put milk and cereal together, right? Well, if you go to the supermarket, you find milk over here and cereal over there. The reason is they know that milk and cereal go together so well. People who walk through chocolate, bananas, and apples, right? So this is one of the most, if you want to say, practical, right? So it's very primitive technique. It's just literally counting. Okay? So frequent item set mining. Why is it called mining? It's precisely because the volume of data is huge, right? So, oh, there's a combination, and I think it's that that combination has been very powerful. It's been the game changer in the grocery business, at least, because that is the most typical application. Lots of product types, lots of volume, lots of transaction, steady data stream going back 20, 30 years. Yeah. And that's also why, well, certainly they might not be able to go down to nitty-gritty brand of product, but certainly by type of product. And this is maintained by a dictionary that maps the SKU. You know what SKU is? It's the identification of product type. So if you sell a straw that has an SKU, a cup has another SKU, and so if straw and a cup belongs to the same thing like drinks, serving, yeah, then will be in category, the entire category, so forth. Yeah. So the top category in a supermarket may be something like perishable versus non-perishable. I don't know how supermarkets do it, but that's that. So they don't have to go all the way detailed to bananas and oranges. They can be something like perishable and something with a shelf life. Most likely they'll do something more detailed because they have computed one. Okay, so frequent item set distributed that, and we're going to show how it works a little bit today. Now, I just want to give you the heads up on the rest. I don't want to spend that much time. Okay. The second one is for association rule mining. It's a little bit like that, except it's phrased in terms of conditional probability. Now, conditional probability you should already be familiar with, but we can give you a sort of like a review after that. So instead of saying something like this banana apple combination accounts for 1% of sales, which is a lot because you have, after all, a million combination, right? 1% of a million is a lot, right? It's out of market. Yeah. So you say that that's a high proportion. Now, the rule in this sense is the X to Y thing. Okay? So it's analogous to what we were saying earlier. Where are things? Where are the X? That would be the item set. But if I know X, do I know Y? That's sort of like the second analysis. This is the rule thing. Given that this basket contains apple and banana, what is the proportion, which is interpreted as probability, that it will also contain orange? Right? So right away you can guess. Given we have apple, banana, probability to contain orange will be higher than given apples, banana, probability is going to contain cigarettes. Okay? And that you can say. But in general case, you can't. And that's what this is. Okay? And there will be some technical term like support, like the number of positive case and all that. And if you're really interested and you want to do that to a project, then I'll leave it to part of the project. In real life, it's done by what's called, most of the time it's done by what's called a priori algorithm. It's like a written algorithm, I think in Python, already well implemented. Okay? And you just feed that through and it gives you all this number. Now, sequential pattern mining is a little bit different. It's not the pattern in one basket, but basket across time. So you can say something like one basket being apples on Monday and bananas on Tuesday, right? So that's like a basket of time. There's a sequence. There's a sequence to it. Yeah, there's a sequence to it. And likewise, when you go down to sequential rule mining, it's the same thing. We said it into a conditional probability. Given that you have apples and orange on Monday, what's the probability or what's the likelihood it's going to be followed up by orange and pineapple on Thursday? Okay? Now, by the way, what's followed can also be set, not just one item. Even apples and banana, what's the probability this guy will buy orange and apple and something else? And even the same thing, even the repeat item. You can have repeat items now because it's a cross time, right? Apple bought on Monday, it's not the same thing as apple bought on Thursday. Okay? So that's that. That's basically it. Okay? It's powerful, it's ubiquitous, it's used a lot in the industry. Okay? It's boring, okay? It's been around forever, but it is powerful. It is powerful, okay? And it actually literally determines what your shelf, what your supermarket looks like. It's not by accident, okay? There's another thing, by the way, that's not by accident. It's the shelving space, you know? If you take an experiment, if you go to two stores, say Big C or Lotus or whatever, in a typical neighborhood, typical common area, so that they're not different. Okay, it's not like an upscale Tesco versus downscale Lotus, but sort of like similar neighborhood. If you look at the shelf, it would have kind of similar kind of profile, like what's on the top shelf, what's on the middle, what's on, okay? Now, it may also be different because people who sell to those stores actually bid for space. So the difference is not necessarily just due to the store manager wanting to promote certain product, but it's also the bidding, okay? Yeah, go. So that's that. So that's that's what we mean by good old-fashioned data mining. Okay? I don't want to be rude and write old-fashioned in it, but it is what I consider it. But let's see how it kind of works. It works a little bit like this. And this is why I want to tell you that it looks like a word count. Now, here, and you have this on your CDF as well. I just load from this data site, okay? And it's sort of like repository of data that you can play around with. A bunch of things, right? So you can actually play with this and use that as part of your project if you wish. Okay, there's a lot of that, and this one I think is from retail. It's from this thing. All right, basically that's what I mean by a basket. This guy bought the first 29 items. In this case, the number is the product identification. Think of it as a SKU. Okay, so the first guy bought all 29 products. The second guy bought 30, 31, 32. The third guy bought this. And the 10th guy bought this, right? Now, this is not very deep, but it's very big. Okay, let's see how big it is. 88,000 baskets. Okay, now, never mind. You're not going to have all the combinations. You know why? Because if I flatten the data comes in basket form. So I flatten to basically list all the product, and I take the maximum because it goes from 0, 1, 2, 3. I want to know what's the maximum product number that is. So actually there are 60,469 products available. So how many combinations of basket can you have? It's 2 to the that. And remember 2 to the 100. Okay? This is what we call combinatorial. We can't explore them all. So let's find tools that would help you analyze. Okay? So now, this built-in function called count create an association. Now remember I told you guys that Mathematica, the most fundamental object is list of number, right? And the second most useful is called an association, basing a map. Instead of you have a list that if you give the first name, it gives you the output. So this is called key, this is called value, right? So the count function gives you an association of product ID to frequency. Okay, so basically it's counting. Okay? Out of 88,000 baskets, how many times does 0 occur? That's the frequency of 0. How many times does 1 occur? That's the frequency of 1. Okay? So this has kind of been optimized through some kind of counting algorithm. Okay? So it's giving all this rule. So out of all this, 0 occurs 177 times, 1 occurs 266 times, and so forth, right? That's a lot. So let's see. Now, I want to know just the values of the frequency. So it's a frequency of frequency, okay? So I do a histogram. Histogram of the value of the association, there. So most of the items occur with relatively low frequency. So you can see that 0 up to 50, right? So this would be like how many items occurs 0 to 1 time. How many items, that sort of thing. I don't know how fine the bin is. Okay, I think the bin is about, what is it, 5 at a time. So it's 0 to 5 times, 6 to 10 or something like that, roughly speaking. So that's a lot. That's a lot. Now this is a programming thing that I want you to learn. There's a function called select. Okay, this is like database programming, like SQL. Okay, but it's more powerful because you can apply any kind of rule, any kind of generalization. I want to select from this thing, from this association, anything that's bigger than 1. Okay, that value is greater, sorry, 1,000. In other words, the products that don't sell very much, right? I would not care. Okay, and I just want to know how many there are. And this is my shorthand. I assign the list to this, the association to this, and I take the length. So I'm doing two things at once, okay? That's just to make things look short. So there are actually 56 products. So here you have 1,600 and some odd products. 56 of them are really your money maker, are the things that you sell over 1,000. Okay? So that's how you select. Now, let me see what they look like. Let's do the histogram, but just for these guys, the top item. Okay? So see the frequency? So it's over 1,000, right? So it's 1,000 to 1,500, 1,500 to 2,000, and so forth. Okay? Now, what I like to do also is, if you notice, this is ranked by 0, 1, 2, 3, by the ID, by the key. I want to rank by the frequency, okay? And in fact, I just want to rank this guy, the top item. So I'm going to say sort, and I give the function. So this is like a very powerful, more powerful way than doing database programming. So count the item by comparing greater than, okay? So it gives you the 56 product, the product number 39 sold over 50,000 times, all the way down to the product 19, which sold 1,005. It's greater than 1,000, but just only 5 bigger. So this is rank, right? This is rank. Okay. This is just my checking something. Okay. So I want to know, in this case, let's say I want just the top 5. Let's look at the top 5. So basically, it's this guy, right? So I take the keys of the top 5. So that's 39, 48, 38. Yeah, so it's this guy, 39, 48, 38, 32, and 41. Okay. The reason I want to focus on just 5 is because I want to do the basket now. So I need a little more smaller. That's into the 50 before, right? So in terms of top 50, I got top 50. Now I want this top 5 combination. Okay, combination from the top 5. So how many can I have? 32, right? Now, the reason I put this 2 is because I know the first one will be an empty set, and I don't need empty set. Okay, so that's all. So if you count this, it's not 32, it's 31. I don't care about that. So these are the combination, of a basket of 5 or less. Think of it as a basket has a space. You not to make 5. So you do 5, 4, 3, 2, 1. You can pick 0. Okay. So now there are 31 combinations thereof. Okay. Now what I like to do is do the same kind of analysis, like how often, but not just a single one, right? I want to count combination. Yeah. So I do what's called sequence count. A sequence count is like when you do the count, you find the individual value, but in sequence, you apply this. You apply this as a sequence. This happens to be a sequence of 1 product. This happens to be a sequence of 2 products, sequence of 2 products, right? So I'm applying the sequence of products. Okay. There it is. So apply to that. Good. So 39, okay, appears here. Now this doesn't mean that 39 only. It doesn't. I think it counts this as well. For example, 39 here and 39 there. So obviously, okay. Let me. This is not mutually exclusive. In other words, if 39 appears as part of a basket, it also counts as itself. Because after all, we don't care about, you know, mathematical partition. You care about how popular the item is. So you get this. So what I do is just make this into an association, And you can follow this later and turn it into table form just so it looks nicer. Okay. So now, apparently, nobody buys all 5, even though they're all popular products. Nobody buys all 5. There's only one for combination of product that gets sold, and that happens 4 times. Okay. Right. So obviously, if you look at singlet, it's a lot more. Now, if you say, if you want to do some kind of this is done. The analysis is done, but in terms of business implication, you can do anything else. The marketing people will say something like, well, if I want to do something like buy 2, get something, or something like that, right? What are the popular 2? What are the most popular 2? It is 39. Actually, it's not the most popular 2, it's the most popular 2 from the 5 most popular 2. Right? So this kind of back and forth between data scientists and marketing team can go on forever. Yeah? So they can interrogate what is that. I like to use the word interrogate a learned model. A model, a machine has learned the data, representation, and then we need to interrogate information. So that's it. And of course, if you're talking about rule, then it becomes something like instead of this probability, it's probability of 38 given you bought 39 or 40. So it's extended, it's more complicated. I'm not going to spend more time on it. If you want to learn more about like sequential pattern mining, sequential rule as part of your project, certainly this will come up. Okay, but as a overall class time, I think I've spent enough time on it. Okay. So let's cut it back. Okay. Now let's go to outing. So supervised learning. I like to say that supervised learning and unsupervised learning kind of does 2 things. Yeah. If you are going to look at the population and see the distribution, it kind of makes no sense to use machine learning per se, because in a way, statistics has done a great job. Statistics has been around 300 years. So there are enough distribution families out there to fit anything. And push comes to shove, we always use what's called like empirical distribution. Yeah, that's like using the histogram as your model. Yeah? You can also do what's called kernel distribution. If we have time, we might come back and talk about it. But basically, as a machine learning problem, which is the problem with the one as a data analytics tool, is what I call 2 things. One's called data partitioning and one's called space embedding. Now, this is not universal term. Okay? Some people would say, well, I would use cluster analysis versus dimensionality reduction. I consider those things sort of like a refinement of the concept. The concept of data partitioning is to say, well, not all, we have one population, we have one sample. And ideally, that sample represents the population. So you can draw some conclusion from looking at the sample. However, it turns out that when you collect the samples, you're not collecting homogeneous entities, because you're actually collecting something that has natural separation. Right? In other words, I think I'm collecting a generic human being. Generic human being. And I'm measuring their health. Okay? Right? Let's say I'm measuring n-dimensional metrics, biometrics of the health. And I'll say, I want to look at general population. I want to know what the health is like. But it turns out in this case, in this group or in this population, in this sample, you've actually been collecting from two different kinds of people. There are health-conscious people, and there are the people who don't care about their health. Okay? Or maybe there's another population that you were drawing the sample from. It's the people who are health-conscious, but because of accident or old age, they become debilitated. So their health metrics don't look good, but they actually do the best they can with respect to everything else. Cholesterol count, whatnot, as much as they can. So let's say you have three populations. Naturally, when you draw samples from there and you measure, you will notice that they are not all together. They naturally cluster. Okay? That's why a lot of times people just say this is a cluster analysis. But I would say it's not partitioning. Because when you say clustering into three groups, partitioning. Okay? So you kind of partitioning. And the implicit idea is that, yes, we were trying to get information on this population. But no, before you go ahead, you have to realize you can't treat them all alike. They're not all different, but they're not all alike. But there is a rough categorization. There's a rough, there's a homogeneity within each cluster, but not between. Yeah, so three kinds of people, three kinds of health people. Yeah, healthy, unhealthy, and trying to be healthy. Let's say something like that. Now, the narrative, the wording, the terminology of healthy comes later. Yeah, the machine doesn't know, and that's the whole point. Okay, pay attention to this. I'm not classifying people into healthy, unhealthy, or trying to be healthy. If I was to classify them into healthy, unhealthy, and trying to be healthy, that means that in the data set, there is a tag that says this guy is healthy, this guy is not healthy, this guy is not trying to be healthy. That becomes what? Supervised learning. There's a tag, right? There's a tag. This one, there is no tag. In fact, the computer output is group 1, group 2, group 3. It's when I analyze the individuals within group 1 and look at where they are with respect to the mean health number. This group, the average cholesterol number is very low. Yeah? Triglyceride and green levels is within limit. And then you look at this group and say, oh, the sugar is all over the place, cholesterol all over the place. Then I'll start naming these people, you know, body abusers, something like that. But the tag comes later. The tag comes later. Yeah. Then maybe I look at the other group and say, I usually have a lot of good biometrics number, but something is usually off. Maybe the kidney is off or the lung, something like that. So maybe this guy is sick or something. He's trying to be healthy but sick. Yeah. It's kind of the doctor. The narrative comes later. So that's what that is conditioning. Think clustering. Okay? If you want to talk to your friends, you can use the word clustering. I don't care. Okay? The other one is called space embedding. Now, space embedding is a very difficult concept to get your head around. But basically, think of it this way. If I have 2 dimensions, you guys live on 2 dimensions at the moment, right? Because you can't go up and down. You can sit on the floor. So this is the axis, X. This is Y, right? X, Y. Now you guys are nicely distributed, evenly distributed, right? Uniformly distributed. So in order to address you guys, I need 2 numbers. The third, the right table, 2 back, whatever, right? So I have to say, you know, 1, 2, 3, 4. How much? 1, 2 get to you. I can't use 1 number. Yeah, I can't use 1 number. Okay? 2 dimensions, I need 2 numbers. But for some weird reason, you guys just sort of like line up in a line. Have you seen that? Well, when you look at the motorcycle taxi line, sometimes there's like electric power power line or whatever, like a pole, and it's giving a shape, yeah? And then the first guy will stand here, the second one here. So even though there's like space all over, yeah, they all line up. Okay? In that case, I only need one number. As long as I walk from the line of the shadow of that telephone pole, I can say 1, 2, 3, 4, 5. So even though the space is 2 dimensions, they actually live on 1 dimension. And in fact, go back to you. The space is 3 dimensions. I only need 2 numbers. Because none of you can levitate. Yeah. So already, you're not using your space efficiently, right? I say, well, spread out. If I say spread out and you have superpower, using a Eggman or something, then you guys will be up there and down here and so forth, right? Social distancing, with mutants or something. But you guys are not, so you are constrained. So your dimensionality is in fact 2, not 3. Just like the people waiting for motorcycle cabs, they live on a 1-dimensional data manifold. I'm just going to say that word, I'm not going to say it. Yeah, that's good. You don't need to use that word. You will annoy your friend. So this kind of thing. It is the analysis that really the data. Okay. Now they're similar to data conditioning. Why are they similar? Well, it's similar to saying that they're not using the whole space. They both arise from the fact that it's not using the whole space. Right? When I say you clustering, you're not using the whole space evenly. Because you like to be in this corner, and the other cluster like to be in that corner, and not in those corners. But it turns out that your corner, maybe over here, and their corner, because they are mutants, they actually levitate. So even though they're 2 clusters, you're using the whole space, right? You're using the whole 3-dimensional space. So you're going to do that as well. And the second problem is, well, let's say there's only 1 cluster. So it's not centered to just 1 cluster. But that 1 cluster only lives in 2-dimensional subspace, 3-dimensional. Right? So these 2 things are not are kind of like complementary concepts to analyze it. It all has to do with not being evenly spread out through all the combination of values across all dimensions. Yeah. 1 is about bunching up, so it's not uniform distribution. The other, and bunching up, there are more bunches. That's 1, right? And the other one is about, bunching up so that you restrict yourself to lower dimensions than you could. Yeah, you could use big dimensions, but you constrain yourself down to 2. Yeah? And space embedding or dimensionality reduction is about trying to find that. Yeah? It's like saying this room is 3-dimensional. The answer of the analysis is to say the 3rd dimension is irrelevant. Only 2 dimensions that matter. Okay? So you are reducing the dimension, but you're not losing anything, right? Right? Just like the space around the axis cube, right? You can literally do anything you like to the area to the side, and it's not going to trouble the people standing, right? So you only need 1 dimension to place your data, even though you have 2. And that's the 2 problems of unsupervised. Yeah. Now notice why this is different from statistical method. Well, with statistical method, if you have 3 dimensions, you kind of like mostly assume you live in 3 dimensions. If I have a bivariate normal, you have 2 dimensions. If you have a 3-dimensional multivariate, oh, you live in 3 dimensions. Yeah, it's like a ball in 3 dimensions. It's an ellipsoid in 3 dimensions. You have 4 dimensions, it's an ellipsoid in 4 dimensions. right? And how many clusters? Only one, because the normal distribution has to be out in the middle. It doesn't have a little one, right? You guys remember the old geyser, old faithful geyser example? That's from visualization class. You done that, right? You remember that, right? This guy, remember that? Yeah? Now, this one, in theory, I can do it with statistics because when I find it, it looks very nice like a normal shape, bivariate normal, and there are two of them. So I can fit it with two normal distributions. So like a combination of both, right? But this is not normally the case. When the data is scattered all over the place, it usually doesn't have a nice shape. But this would be the case where you can do clustering analysis with traditional statistics. Yeah? Just in this case, it's special for that reason. So I will use this sample forever to teach everything. Visualization, traditional statistic estimation, Bayesian model, and machine learning. So this example is important. Yeah, this happened to me. Yeah, but most of the time, it would have a very messy picture. Right? It's not a nice lump here and a nice lump there. It's maybe a nice lump here and this cigar chain there, that sort of thing. Okay. So, are we on the same page? Okay? If we are on the same page, I'm just going to talk now about clustering. Okay? First. Now, in this case, I will actually go to, let's see. I'll give you a break from Mathematica because this page is nice. Cluster analysis. Right. Again, ignore the color. This is just your data. Yeah? In two-dimensional plane, you can definitely see. In fact, it doesn't make sense which one works best, right? If you want to say, I want the clusters to be differently colored, you would say that this one is nice, right? The inner circle versus the outer circle. But this one is no good because it's kind of like mixing this, right? So these are all the different clustering techniques on the same test data. These are artificial test data. I do that a lot for myself, creating artificial test data, just to highlight the feature. So in here, all you need to know, when you do your project, you will be programming and you'll be doing all kind of stuff, right? But the first thing you need to know is that there are two types of clustering. One is based on distance. That's who's going to move. In a global setting, you are going to be person or part of that person. Right? The other one is about contiguity, like density. So if you imagine, I just want you to look really closely at this guy, at this example. This point and this point are very close to each other, right? But in fact, in terms of density, you are more densely connected with these guys, and in turn, you know, a whole connection going down the line to here, than you are to these people. It's as if there's like a natural barrier, like there's a river or something. So you can imagine, yeah, if you have two populations across the river, yeah, this is one mountain, this is another mountain. People on this mountain are not close to people on that mountain, right? Because there's a river in between. But if you measure distance in 2 dimensions, like if these guys have helicopter or something, you would say this guy is close to that, okay? So that's the two main types of cluster analysis: distance-based and density-based. And I would say, let's say for your project, okay, you would use something like k-means, agglomerative clustering, dB scan, maybe Gaussian mixture. But certainly k-means hierarchical อยู่ใน agglomerative ใช่ไหม Technically hierarchical can be agglomerative as well as top down, but okay. So you have agglomerative ก็คือ hierarchical from bottom up. Yeah. Okay. I would use a more generic term, which is hierarchical clustering, k-means and dB scan. dB scan, the D stand for density based. Okay. Now you can find all this. K-means, yeah, k-means agglomerative, dB scan. Now, what is unfortunate about some of these algorithms that you need to kind of guess ahead of time how they cluster it out. If it's agglomerative, you don't have to guess. You don't define from everybody in a single cluster. And if you close it up, so you don't have to tell the computer. You go to agglomerative. It's agglomerative. Yeah. ทำไมต้องใส่ n cluster ด้วยล่ะ I don't think you should. ไม่ต้องใส่ n cluster ด้วย Maybe hierarchy. Huh? ไม่แน่ใจ Something looks fishy. Anyway, but definitely things like dB scan and k-means. K-means is distance based, but based on fixed number of cluster. Now, because you have to specify the number of clusters, yeah, you will do what I call elbow analysis. It's heuristic. How do you tell that the computer is doing well? In the question, you have what? The data point is different from the model, right? Yeah. Residual error, you minimize that. How do you tell that the cluster model is doing well? Well, let's go with the distance base. The distance base, right? Distance base work really well in this kind of problem. So, how do you know that this one is doing well? It's doing well because the distance from those within the same cluster is small. The distance with those from other clusters are very large, right? In fact, that's how the algorithm is designed to optimize. It's minimizing the internal distance, the intra-cluster distance, but maximizing the inter-cluster distance. The k-means algorithm means to start with k random center. And then you say, well, for this center, let's say who's my closest, that's my cluster. For this center, who's my closest, that's my cluster, right? And then the algorithm literally moves the center so that you minimize this within distance. Right? And sometimes the data point will move cluster. It used to belong to this cluster. Now that the cluster center of the other cluster moved, you are closer, so you go over there, right? Just like a center of the factor moves, right? Except there's no like social influencer. It's just the average of that. It's an artificial, it's called central. And the algorithm ends when you have 3 centroid, 1, 2, 3 at the center. And that's when you start to give the name. Because you look at the centroid and you say this centroid representative of this cluster has high cholesterol number, smokes a lot, has high sugar. So this is the body abuser, right? Whereas the guy is a runner, healthy, resting heart rate of 70, 65. They say, oh, this is a health map. Okay? But you only get the name afterwards. This is unsupervised, right? Unsupervised. So that becomes your the analysis, the result of your analysis. This then, imagine that. Now, you can't see this picture because it's not two-dimensional, it's n-dimensional, right? So obviously, you have to have some kind of criteria. For example, if k is equal to 3 I get certain of this between the two. Don't forget this between two. This is the two. How do you minimize that? Let's say you allow to change the number of customers. The minimum is what? It's equal to the number of data points, right? Because if you are assuming that no repeat, if you are your own cluster, you have zero distance within the team. There's only one person per team, right? So obviously, if you keep minimizing the distance, the best solution would be to have as many clusters as a data point, which is silly. So this is why you do this kind of block. 2 clusters, 3, 4, 5, 8, 8 is in block 2, 3, 4, 5, 6, 7, 8, 9, 10. And then you look at the distance is going to drop down rapidly, then it's going to taper off. Now, heuristically, it looks like an elbow. It looks like an elbow. So for the first few K, the within cluster drops very rapidly. Then it starts to slow down. So this is what they will use. It's the elbow method. Literally something. Hacksaw. Yeah. And there are way of coding this. Sort of like if you have a origin here, sort of like keep drawing a bigger circle until you get it. Once you get this thing, you say, okay. That kind of thing. Okay. So K means it's not one analysis, it's a bunch of analysis, and then you end up with a K. Okay. And this is there's no, I think in practical term, what you want to do is to separate into clusters so you keep them differently. It's a little bit like mass personalization. You can't personalize your marketing approach to everyone, but you certainly don't want to have one approach for the entire population. But if you know that your population has inherently separated into 5 groups, then you can divide the sales force, your marketing campaign, your product design, your customer interface along those 5 different groups. Right? And then you can also do things like, well, which priority should I give? Right? You can, for example, give priority to the cluster that has the biggest number in your mind. That's obvious, right? On the other hand, you can say that, hey, these guys are already good customers. It's the small cluster we have to expand. So you put your emphasis on the smaller cluster. So how you use it is a business decision. It's strategic business decision. But it is informed by data analytics. Data analytics say, if you want to focus on your current customer base, go with the biggest one. If you want to expand either to undeveloped or negligible sector, go with your small cluster, because that's your growth opportunity. But then you get more here. So the business actionable insight given to business, but the business itself has to decide. And there's a lot of back and forth. For example, you say, well, maybe the business wants to explore the smaller cluster. Maybe we'll ask the data scientists to do something else, do some kind of testing or regression on just this population. It could be a supervised learning problem, but formulated just on this group. Right? So it's not a two-door thing, you go to supervised learning and you go to unsupervised learning, you go to use that together. No, it's a combination of tools, right? You don't just say, I'm going to multiply or I'm going to add. Sometimes you do multiply, sometimes you do add, sometimes you multiply, then add, multiply. Same thing. Analytics tools are modular. But the top thing, the top level technique here today is clustering. Yeah? So that's also interesting thing if you can look at your project. It's a very natural thing to do. Very natural thing to do. And in fact, this is what babies do before they learn by supervised learning. They learn by unsupervised learning. They may cluster things that don't make sense to us. For example, they cluster mother, not with an animal being, but with a dog, because mother comes with a dog. That to us, it doesn't make sense, right? But the child doesn't know that. The clustering is by association, things that come together. So this is that kind of thing. When it's not coming together, it is being dimensionally in terms of space, in that space, growth. Now the density is a little bit tricky because it's not the closeness versus in a general sense, but it's closeness to the next guy, right? That's it. So as long as I'm next to this person, hold this hand, you hold this person's hand, you hold that person's hand. Even though the other person is next to me, right? But there is an immediate distance in there. So this snake can go down a mile. I'm considered closer to that guy than to you. Because through a series of connections, it's a small, it's only like 10 meters to the next person, 10 meters to the next person, 10 down the mile. Versus you, it takes a meter. That's too far. Now that's what it means by density. Yeah? So the algorithm works out differently. My guess is most of the time, well, anyway, my application, if you're working with a lot of summarized statistics, then distance-based clustering is good. But it's always good to check. The problem is, of course, you can't visualize it. Now, let's go to, and you guys okay with this now? So now I'm going to go to the second. Second one, again, is about studying the space. There's actually two problems there that I bunched together. In fact, dimensionality reduction and space embedding, to me, are distinctly different. But a lot of times we treat it the same way. Let me tell you what I mean. If I determine that you are not using all the 3 dimensions available to you, I'm going to say you are a 2-dimensional object. Okay? That's like, space and time. But the technique for doing that, is to map your 3D coordinate into 2D coordinate. In this case, it happens to be easy because the third coordinate is always 0. It's always on the ground, right? It's easy, right? But mathematically, it always means I'm transforming a 3-dimensional vector into a 2-dimensional vector. The technique. Now, how do you transform a 3-dimensional vector to 2-dimensional vector? One way is to multiply via 2×3 matrix. Yeah. Now imagine, what is that this 2×3 matrix? What is stopping you from using this matrix on 3-dimensional objects that are themselves occupying all 3 dimensions? Nothing. Right? Original motivation was that I only need 2 dimensions because you don't use your space. You don't utilize all the space, right? So my matrix multiplication is 1, 0, 0, 0, 1, 0 because the last element. Can you imagine that in your head? Yeah? 1, 0, 0, 0, 1, 0. When you multiply by a 3-dimensional vector, you just get rid of the third one. That's it. All right? But I don't have to use just that matrix. I can use any matrix. And once I have that matrix, for whatever reason, I can apply to any 3-dimensional object. Even if you are in the air, I still can do that, right? The end result is to put a three-dimensional object in two-dimensional. Not because you were naturally two-dimensionally aligned, but because I made you. Okay? I literally forced you. So it's a little bit like you are spread in three dimensions. Yes, in the some of you are in the air. But I choose to look at you from the top view. And I just press everybody down. You go down. Okay? Or I come over here and say, you go to the back, to the wall. So I just force you. Now, this forcing is called dimensionality reduction. Okay? Now, this forcing like this is heavy-handed, right? It's just say ignoring the third dimension. That's not good. That's not good. Now, I want you to look at this. Imagine, okay? Imagine. Oh, this is hard. Okay, this is good. Okay, you have one group here. Okay, one group here. Okay? And then very high up, there's another group that's also like in a circle. Okay? Yeah, what's my hand, guys? Look at my hand. Yeah, there's a bottom dweller, there's a top dweller, very far apart. Right? They both live in three dimensions. Balls. If I just brutally look here and I think, everybody go down, I'm going to get rid of the third dimension. You land up on top of each other, right? You be indistinguishable. That's no good. What if I can do this? I can kind of like squish you in two dimensions, but do it in such a way that you separate. Yeah? So you become two-dimensional animals, but in the coordinate that maintains a separation. Right? Right? So it's not a blind dimensionality reduction. I don't just get rid of the third dimension. X3, X2, or X1. That's just squishing. I'm actually doing a thing that has a magic property that I squish them, but if you were separated in three dimensions, you are separated in two dimensions. In fact, it's this property that you are preserving. Sometimes it's called topological preservation. You're kind of preserving some quantity. In this case, if you were neighbors, if you were in three dimensions, and you were strangers in three dimensions, when I squish it into two artificial dimensions, you're still strangers to the same people and friendly or familiar with the same people because you're close. So this kind of dimensionality reduction is really powerful. Yeah? So you can say that this kind of dimensionality extraction has different interpretation. One is naturally you are in the low dimension. The other one is, yeah, you're using it, but I want to, I can't optimize it. So this becomes, quote unquote, the first thing you can think of it as a visualization tool, right? And this is one of the first applications in macroeconomic analysis of countries. You can literally take a country which has 30 dimensions: employment, education, geographic, land area, blah, 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 blah. So 30 dimensions, right? Which you squeeze them into a two dimension, voila, Thailand is close to the root. Because in 30 dimensions, we are closer to the root than we are to Cambodia and Myanmar. Okay? Because we're closer to Cambodia and Myanmar only in geographical distance. There is a distance to GDP, education, all kinds of stuff, right? Crime rates or whatever. Social equity, income distribution, Gini index, all sort of stuff. So you can switch all that, right? And you will do that. Yes, you can say Thailand is closer to Laos. Yeah? So this is extremely powerful. Now, I'm just giving you a description. I'm not giving you any algorithm here. Okay? But again, if your project is cluster analysis, then I would recommend something along with hierarchical. Hierarchical means there's a natural clustering all the way down to one. Okay? But if you start from everybody belongs to the same cluster, and then you divide that one code, the other code says everybody is a single cluster and you can have along with it. But they're both hierarchical.